the main sequence.
So our sun is in the main sequence. We're very happy it's in the main sequence. It provides us the same amount of energy almost every day. And that's what makes life possible.
All stars on the main sequence aren't alike. Some are much smaller and cooler than the sun. Others much larger and hotter.
So it turns out that how hot something is related to the color of the light that it emits. So a star like the sun, most of the light that comes out from the sun is sort of a yellow type color. If the sun were much hotter, the predominant wavelengths of light would come out into the blue or even into the ultraviolet. And cooler stars emit more red light.
Small, cool red stars like Proxima Centauri, the nearest star to the sun, are known as red dwarfs. They can be as little as 1/10 the mass of the sun, with surface temperatures thousands of degrees cooler. Red dwarfs are the most common type of stars in the universe.
There are many, many more of these sort of very dim red dwarfs floating out in space than there are stars like the sun. Now, of course, when you look in the night sky, you don't see the most common kinds of stars. You don't see these red dwarfs because they're so faint. You merely see the very rare, very bright stars that turn out to be very, very far away.
On the opposite end of the spectrum are the large blue main sequence stars. Averaging a surface temperature of 45,000 degrees Fahrenheit, they can be 20 times the mass of the sun and 10,000 times more luminous. In the life and death of a star, size definitely matters.
Mass is the fundamental thing which drives the life history of a star.
The more massive stars live much shorter lives than the less massive stars. And that's perhaps a little bit strange sounding, because the massive stars have more fuel to burn. You'd think they'd live longer.
So it's counterintuitive that more massive stars will burn through their fuel more quickly than the lower mass stars.
Imagine two gamblers sitting down at a blackjack table.
Perhaps a little bit strange.
You would expect the one with the most money, the most fuel to burn, would last the longest.
That more massive
But what if the big-time gambler is making huge
stars will burn through their fuel?
Bets on every hand?
A gambler that is gambling with a lot more money and putting down $10,000 at a time is going to burn through that money much more quickly. And so the more mass you have, the higher temperature, the higher pressure, the higher the fusion rate. And it goes much more quickly with the more mass you have.
And it's always just simply the calculation. How much fuel do you have? And at what rate are you converting it? The high-mass stars live their lives faster. They burn the candle at both ends. There's life in the fast lane. A high-mass star could die within 1 million years.
A star 10 times as massive as our sun might live for only 1/1000th as long. So our sun will live for about 10 billion years in total. A star 10 times as massive as our sun might live only 10 million years in total.
While massive stars have lifespans measured in millions of years, the lowest mass stars measure their lives in tens of billions, if not trillions of years.
Every low-mass star that has ever been born in the universe, and the universe has been making stars for more than 10 billion years, all of those stars are still in their infancy. No such star that's ever been born has ever come close to dying.
But for all stars, including our own sun, life on the main sequence can't go on forever. It can only last as long as the star has fuel to burn. If it runs out of fuel, fusion stops and gravity wins.
Gravity never gives up, whereas fuel, of course, can run out after a while. And so the star and the climber both have this terrible problem that if they don't maintain their fight against gravity, they will end in a death, a cataclysmic death.
Not only does the size of a star influence how long it will live, it also determines how it will die. Massive stars explode from the scene in violent fury, while smaller ones are doomed to slowly fade away. For 5 billion years, our sun, a lower mass, middle-aged star, has been happily burning through its supply of hydrogen fuel, like a gambler slowly plowing through a pile of chips.
The gambler, you may sit there for a long period of time, just like a star burns its hydrogen for a really long period of time. However, at some point, she's going to run out of money.
Scientists predict that 5 billion years in the future, our sun will reach this critical crossroads. Its supply of hydrogen fuel will have been completely exhausted. Nuclear fusion will cease, and gravity will begin to crush the star. At that point, the situation is desperate. In order to survive, a sun-like star must find a new source of fuel. It has helium on hand, but in order to start burning helium, the core has to be 10 times hotter than it was during its lifetime burning hydrogen.
It won't be able to fuse that helium into heavier elements like carbon and oxygen until the core gets sufficiently hot. And that's because it's harder to get the helium nuclei close enough together for the strong nuclear force to take over, grab them, and cause them to fuse together.
As it continues to contract inward, nature throws the star a lifeline. The core actually becomes superheated by the very gravitational pressure that's trying to crush it. When it reaches 180 million degrees, it can start fusing helium into carbon in a desperate gamble to survive.
So the desperate gambler might go take out a loan on their house and get more money. But in getting more money to burn through, it's really just delaying the inevitable, which is to go bust. And for a star, the inevitable is to die.
The star, which took 10 billion years to burn through its hydrogen, now powers through its supply of helium in a mere 100 million years.
And then the action begins. runs out of hydrogen. Starts fusing helium. Runs out of helium, attempts to fuse carbon and will fail. But all the action, all the, well, what's going on now, happens in the last 10% of a star's life.
The searing heat of the helium burning actually causes the outer layers of the star to swell.
At that point, the outer atmosphere of our star will be held in by gravity so weakly that it'll start sort of just evaporating away. Through a series of what I call cosmic burps, it will actually eject the outer envelope of gases, which are only weakly held by gravity. That'll send some shells of gas outward, illuminated by the hot central star. And that will cause what's called the planetary nebula phenomenon. Beautiful shells of glowing gas surrounding the dying core of our sun.
With the core unable to muster any more nuclear fusion, can it possibly survive gravity's crushing grip? As a star the size of our sun dies, it ejects its outer layers. With no nuclear reactions to generate outward pressure, gravity gains the upper hand. The star begins to fall in on itself, like a climber too tired to hold on to his rope.
There's one possibility that the rock climber might be able to use if he gets too tired to hold on to the rope anymore, and that is if he can find a ledge on the rock that he's climbing. Gravity can pull on him all he wants, but the ledge itself will support him against gravity, and he doesn't have to provide any more energy to win his fight. There's a certain kind of star, and our sun is actually an example of this, where the star finds that it has an out in this fight against gravity.
The contracting star finds its ledge in a surprising place: electrons. Tiny negatively charged atomic particles.
Electrons don't like being compressed so that they're very close to one another, because electrons effectively don't like each other.
If you compact the electrons hard enough, the pressure of the electrons themselves is able to hold up the star against gravity.
When the core of our Saturn's moon sun-like star seems to have the necessary ingredients of the Earth. Annihilating at the University of Colorado has shown that when sun called electron degeneracy pressure takes over, gravity can collapse the star no further. The University of Colorado has shown that when sun called electron degeneracy pressure takes over, gravity can collapse the star no further.
Now, usually there's nothing new in the new picture, but occasionally
University of Colorado
a star blows
has
up, a supernova goes off, And then you can see in the new picture a bright point of light that wasn't there
Shown that when
in any of the old pictures. Though a supernova is visually very, very bright, the visible light is only 1%
electron
of
degeneration
1% of
takes
the total
over
energy.
and collapse the star no
1/10,000th
further.
of the entire energy emitted by this colossal explosion.
Although Type
Now,
1A
usually there's nothing new in the
supernovas
new
come from
picture, but
exploding
occasionally
University of
a star
Colorado,
blows up, a supernova
many
goes off,
others, known
and then
as
you can
Type 2
picture a
supernovas,
bright
signal the dramatic deaths
point
of
that
much more
wasn't
massive
there.
stars, perhaps 8 or 10 times more massive than the Sun. Unlike their smaller cousins, when massive stars exhaust their hydrogen fuel, they have the raw power to start fusing other elements. The ashes of each set of nuclear reactions become fuel for the next. So that near the end of its life, a massive star resembles an onion in cross-section, with an outer layer of the original fuel, hydrogen, surrounding layer after layer of heavier and heavier elements.
It goes through its normal life, fusing hydrogen into helium, then helium into carbon and oxygen, then oxygen into neon and magnesium, and then silicon and sulfur. And then iron. The massive star builds up a core of iron. But fusion of iron into heavier elements doesn't do the star any good. It doesn't keep the star hot inside, because fusion of iron into heavier elements requires energy. It absorbs energy. It doesn't liberate energy. So the iron core builds up without fusing and eventually becomes unstable. When it reaches something like 1.5 times the mass of our sun, it collapses.
And the collapse is violent. Within half a second, a core the size of the Earth is crushed into an object roughly 10 miles across. For a moment, the collapsing core rebounds, smashing into the outer layers of the star and kicking off one of the most massive explosions in our universe since the Big Bang.
The collapse of the iron core blows apart the rest of the star in a colossal explosion. It's truly an amazing, incredible event.
Scientists are convinced that supernovas mean much more to the universe than spectacular light shows. They are, in fact, the source of the heavy elements that make up everything around us.
All of the iron in this foundry came from exploding stars, from gigantic explosions. All of it. All the iron you see everywhere came from exploding. Stars. And in fact, all the elements heavier than iron directly or
come from exploding
indirectly were made by
is violent.
exploding stars. The collapse of those elements were ejected into the cosmos by these gargantuan explosions.
As material from these explosions spread out through the universe, it became the stuff of planets, moons, new stars, and something even more extraordinary. Come from exploding. If you could trace your ancestry back to its earliest reaches, you would find an exploding star in your family tree.
We are essentially made of star stuff, or stardust, as Carl Sagan used to say. The elements in your body, not just generically, but specifically, the elements in your body, heavier than hydrogen and helium, came from long dead stars. The calcium in your bones, the oxygen that you breathe, the iron in your red blood cells, the carbon in most of your cells, all those things were created in stars through nuclear reactions and then ejected by supernovae. And the heaviest elements, iron and above, were produced by the explosions themselves, by the supernovae.
While the explosion of a Type II supernova showers the universe with heavy elements, the core of the exploding star is left intact. Destroying that is gravity's job. But to crush the core any smaller than the size of a white dwarf, it will have to overcome that strange force, electron degeneracy pressure.
Gravity actually finds a way of defeating that tendency the electrons have to push each other apart. By combining the electrons with the protons and turning them into neutrons, you now have an object which is made almost entirely out of neutrons, and gravity wins. It now allows the system to collapse further. There are no longer electrons stopping that, and gravity seems to win, except neutrons, it turns out, also don't like each other, and you end up with a new stable object, even smaller, even more dense, called a neutron star.
Compared to normal stars, neutron stars are cosmic pebbles. They can be as small as 10 miles across.
So imagine you take a star about 1.5 times the size of our sun, and then you compress all of that material down into a very small space, about the size of Manhattan. You've just made yourself a neutron star.
Squeezing that amount of mass into such a small space makes for an extremely dense object. 1 teaspoonful of neutron star material would weigh 1 billion tons.
Neutron stars are some of the most exciting and weird objects in the universe that astronomers study. If a human being were to stand on a neutron star, it would be a somewhat uncomfortable experience. On Earth, if they weighed about 150 pounds, on a neutron star, they would weigh something like 10 billion tons. Our biology can't stand that amount of pressure. And so a human being would essentially be squashed flat against the surface of the star. In addition to that, neutron stars are spinning at an incredibly high rate, hundreds of times per second in some cases.
It's this rapid spin that enabled astronomers to first identify neutron stars.
Some neutron stars are spinning really rapidly, and they have a really amazingly high magnetic field. That magnetic field, together with the spin, forces a bunch of charged particles, electrons, to go along the axis of the magnetic field. And those accelerated electrons give off light. They produce a well-focused beam of light. Now, this is like a lighthouse whose beam is always on, but you only see it when the lighthouse beam intersects your line of sight. In a similar way, we might see the shining neutron star only when the beam points at us. That object is called a pulsar.
Some stars are so massive, perhaps 25 or 40 times the mass of the Sun, that not even a neutron star can hold up under the weight of their collapse. And gravity will crush them even further into an object of infinite density and almost equally limitless fascination, a black hole.
In some sense, a black hole represents the ultimate death of a star.
A black hole is basically gravity's victory over mass. It is complete collapse of a star, a very massive star.
This collapse creates a region of space where matter is compressed into such a high density that its gravitational field is inescapable.
Black holes are remarkable in that nothing can escape from them, not even the fastest moving thing we know of, which is light.
You shine a flashlight beam up, and even it won't leave. The beam will curve back around, so you won't be able to see it from the outside. Hence the name black hole. A common misperception is that black holes just go sucking up everything in the universe. Like that, just like cosmic vacuum cleaners sucking up everything in their vicinity. That's actually not true. Now, objects that are very close to black holes do get sucked in. But if you're comfortably far away with the proper trajectory, you won't get sucked in.
Scientists have long suspected that there is yet another class of supernova involving even bigger stars and even more powerful explosions. Stars that collapse so catastrophically that they leave behind no remnant, not even a black hole. But no one had ever seen one until now. Even after billions of years, the universe is still surprising us with its raw power. In the fall of 2006, astronomers observed the largest stellar explosion ever witnessed by man. 240 million light years away from Earth, a massive star blew itself apart. Alex Filipenko and his team at the University of California, Berkeley were amazed at the power of the explosion.
And the total energy emitted was 100 times as much as the energy of a normal massive explosion. It's an amazing, really powerful explosion.
A normal supernova comes from the explosion of a star 10 times more massive than our sun. Incredibly, supernova 2006 GY, as astronomers have dubbed it, seems to have signaled the death of a star 150 or even 200 times more massive. That's about as massive as a star can get. Scientists are still studying the aftermath of the explosion, but they think supernova 2006 GY has a lot to teach us about the first stars that populated our universe.
We actually think that the first generation of stars tended to be really massive, and they probably exploded by this mechanism.
It's these mega explosions that likely seeded the early universe with heavy elements.
These extremely massive stars are the largest iron factories in the universe. A single star, 150 times the mass of the sun, can produce 20 or 25 solar masses of iron. It's incredible.
In the cycle of life, not only here on Earth, but in the cosmos, as stars die, particularly those that die spectacular deaths, the high-mass stars that manufactured heavy elements in their cores, those give the seeds of the next generations of stars that then increase the likelihood that that next generation will have planets, and planets that contain the ingredients of life itself.
Supernovas aren't the only energetic events in the life and death of a star. Right now, across the universe, there are 1,000 pairs of stars engaged in brilliant dances of fire. For some, this dance will end in catastrophe. Astrophysicist Joshua Barnes of the University of Hawaii studies what happens when stars collide.
We don't have the luxury of watching stars collide. A pair of stars, as they draw close enough to collide, would just be a single dot of light, even in the largest telescopes that we have. So we need to investigate these things with a computer.
Using computer models, astrophysicists can take any two types of stars and find out what happens if they become involved in a stellar smash-up.
The models pose hypothetical situations and then see what happens. And you could sort of imagine this is like studying collisions of cars, and you were taking them out and smashing them together in the parking lot, one after the other, to see what came out of that.
Among the most explosive collisions modeled by astrophysicists is the clash of two orbiting neutron stars.
Typically, they're bound together as a pair orbiting one another. And as they orbit, they disturb the space-time around them and create waves of energy. And the energy to do that slows the stars down so they get closer and closer together. As they get really close together, they're orbiting around hundreds or even 1,000 times per second. The final event is very dramatic.
When two neutron stars collide, they're moving at nearly the speed of light. Although the final collision takes only a fraction of a second, it unleashes more energy than the sun will generate in its entire lifetime. Thanks to computer modeling, we can also predict what would happen if a highly dense white dwarf collided with our sun. It would be a frightening collision.
When it got close enough, the gravitational field of the white dwarf would start to distort the sun, so the sun would no longer remain a sphere. It would sort of turn into an egg shape as this thing came close.
As the white dwarf plows into the sun at supersonic speed, its gravity would send an enormous shock wave throughout the star.
And that would produce so much thermonuclear energy to essentially explode the sun.
Amazingly, it would take only about an hour for the white dwarf to plow through the sun and annihilate it. If this scenario came to pass, life on Earth would be doomed. Fortunately, the chances of this happening are slim because the sun is in a very uncrowded part of the Milky Way galaxy.
Individual stars are kind of jostling and weaving as they make their great circuit around the galactic center. So it's a complicated traffic situation, but because the space between the stars is so great, there's not much chance of a collision. If you were to wait out here on this beach until you saw the collision between the sun and another star, you would wait a long time, even over its entire life. The sun is probably 1,000,000,001 chance of colliding with another star.
But there are places within galaxies where the odds of a collision are much greater. Regions where hundreds of thousands or even millions of stars are crowded together by gravity into a globular cluster. Compared to the spiral arms of the Milky Way, a globular cluster is like a demolition derby. The odds of two stars colliding in the spiral arms of our galaxy are only about 1 in a billion. But within a globular cluster, stars are packed 1,000,000 times more densely than elsewhere in the Milky Way.
In the Milky Way, everybody is pretty much going in the same direction. But in the globular cluster, there's no organized motion. basically all orbiting around the center on orbits which are aligned in all sorts of different directions. So some are going one way, some are going the opposite way.
In these crowded, chaotic conditions, stars collide on average once every 10,000 years. Every star in a cluster was born at roughly the same time. So when astronomers look at an old cluster, they don't expect to see any young stars. But strangely, a globular cluster usually conceals some mysterious strangers. Large blue stars, far younger than the small dim stars surrounding them. These seemingly impossible stars are known as blue stragglers.
The mystery of blue stragglers is that they're, in some sense, younger than they have any right to be. All of the stars of that mass and that luminosity would have died off billions of years ago in these clusters. So the puzzle is, where did these things come from? How did they get into these star clusters?
Astrophysicist Joshua Barnes thinks he knows the answer. He believes blue stragglers are the result of collisions between older, dimmer main sequence stars.
A collision of two main sequence stars, two sun-like stars, is actually relatively gentle.
The mutual gravity of the stars locks them in a spiral.
They've lost energy of motion, and they will come back and have multiple subsequent passages. They heat up and swell up and kind of spiral around each other, making several passes, each closer than the last one, until they finally come together and stars merge.
In the end, rather than triggering a catastrophe, the two stars merge to form one more massive star.
What you're basically doing is taking two small old stars, piling them together to make one star now, which is twice as massive, and therefore being more massive, it's brighter and bluer than the rest of the stars in the cluster. So it seems to be straggling behind the rest of the stars.
While the mystery of the blue stragglers seems to have been solved, the heavens are bursting with unusual objects that dare science to explain them. Black holes, neutron stars, and white dwarfs all represent the end of remarkable stellar lives. But there are other strange celestial objects that never got a chance to shine. Not quite planets, not quite stars. These are the brown dwarfs.
Brown dwarf is basically a failed star.
University of Hawaii astronomer Michael Liu searches for these elusive objects.
Stars produce a lot of light. They're very easy to see a long ways away, but brown dwarfs are very low temperature, and so they emit very, very little light. Because they're so dim, it means we can only see them if they're very close to us.
A brown dwarf has the same ingredients as a star. But it simply doesn't have enough mass to sustain nuclear fusion.
If something is born with less than 8% the mass of the sun, then it can't produce its own energy. It's essentially a failed star.
Without fusion, these failed stars start to act more like planets.
If you were flying in a spaceship across the surface of a star, you wouldn't really see anything that looked like clouds or mountains or anything like that. When you go to a brown dwarf, things begin to change.
We think their atmospheres in some ways might be similar to things like very massive versions of the planet Jupiter. If you're familiar with pictures of Jupiter, you see Jupiter has all sorts of banding structure and clouds on its surface. Although we've never taken a picture of the surface of a brown dwarf, we think brown dwarfs may also have similar cloud structure.
Now, these aren't normal kinds of clouds like we know about on the Earth. You have iron vapor making these clouds. and then the clouds may get thick enough that you get iron droplets raining out of the clouds. Obviously, a person wouldn't want to be there because these are molten iron.
To date, astronomers have located only a couple hundred brown dwarfs, and they still have many questions about these elusive objects. For one, they know some brown dwarfs have disks of dust and gas around them. Might those disks form into planets? That's just one of many mysteries yet to be solved. As we continue to probe the stars. But already, science has revealed the universe to be a magical realm of dwarfs and giants, stragglers and supernovas. And hidden within the explosive life story of stars, they have found the very history of the cosmos. And a key to understanding our own origins.
In the beginning, there was darkness, and then, bang. Giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
In the distant corners of our solar system, ice giants Uranus and Neptune are violent worlds. Blanketed with smoky hazes, these outer planets are frenzied, turbulent, and unpredictable. Neptune claims the fastest winds in our solar system. Like an apparition, its great dark spot surfaces and vanishes without warning. Uranus's inner swarm of moons dash around the planet in less than a day. And collisions are unavoidable. The most controversial of the far-off planets isn't even a planet anymore. So why was Pluto demoted? The man who killed Pluto makes his case as we explore The outer planets. Meet the man who killed Pluto.
Pluto had it coming for a long time.
Caltech astronomer Mike Brown set in motion a chain of events that reduced the long-established number of planets in our solar system from 9 to just 8. Yet he feels no remorse.
There was no way that Pluto could survive its status as the single lonely ice ball, but it was good. It was gonna fall, and it certainly fell.
Among our planets, Pluto was long considered to be a bit different. Much smaller than the rest, it has the largest moon in proportion to its own size. It also has the most inclined and eccentric orbit.
Its orbit is sort of shaped like an egg. Pluto's orbit causes it to get significantly closer to the sun and then further away. The sun.
This cosmic needle in a haystack eluded planet hunters for decades. The 8th planet, Neptune, had been discovered in 1846, and astronomers at the turn of the century were convinced there was a 9th planet in the far reaches of our solar system.
The search for Pluto was started by Percival Lowell at Lowell Observatory. He thought there was a planet X there that was perturbing the orbits of Uranus and Neptune.
Before finding the elusive planet, Lowell passed away. But the observatory's research assistant Clyde Tombaugh continued his quest. In 1930, at the age of 24, Tombaugh captured an image of an object that seemed to validate Lowell's predictions. The discovery was announced to the world, and the object was given an official name, Pluto. But was Pluto Planet X? Some scientists argued that Pluto was far too small and didn't have enough mass to significantly perturb the orbits of its neighboring gas giants, Uranus and Neptune. Astronomers have since realized that there is no such Planet X. It had been predicted using inaccurate estimates of Neptune's mass. Even though Pluto wasn't Planet X, could it still be classified as a planet?
The first term for planet just meant wanderer in the sky. It was the things that moved relative to the stars. So to the ancient Greeks, the moon was a planet, the sun was a planet, the earth was not.
Of course, when we realized that the earth is actually going around the sun and that the moon is going around the earth, the definition of planet changed again. Earth became a planet, the sun and the moon were taken away, and there were finally 6. And over time, Uranus was discovered, and Neptune was discovered. So there were 7, there were 8.
Although it later proved to be smaller than our moon, Pluto was originally thought to be as large as Mars. So Tombaugh's discovery was anointed as planet number 9.
No one really thought much else about it. It was a strange object. It was sort of this lonely oddball at the edge of the solar system. But nothing else to call it, so it was called a planet.
Because of its great distance from the sun, Pluto takes its name from the Roman god of the underworld. At its closest, Pluto is 2.7 billion miles from Earth. Its diameter is 1,485 miles, half the width of the United States. It takes 248 Earth years for Pluto to orbit the sun. And a day on the planet is equivalent to about 6.5 Earth days. A 150-pound Earthling would weigh only 10 pounds on Pluto. It's a testament to modern technology that we know anything at all about the surface of Pluto.
We can hardly see this thing. Even with the Hubble Space Telescope, we get maybe 4 pixels across, maybe 12 pixels total. But even with that, we see that parts of Pluto are as dark as coal and parts of Pluto are as bright as snow.
Even from afar, scientists can measure the composition of the planet. They believe that the bright areas of the surface are made up of 3 types of ice.
Well, one is carbon monoxide, one is methane, which is the same as natural gas. And then the third is nitrogen, the same stuff that we have breathing here in our atmosphere.
The dark areas are probably solid rock.
The darker areas are almost certainly silicates of some sort. Silicates not unlike the rocks that we see here. That means there's silicon in them and there's oxygen in them. We're up here in Rocky Mountain National Park in Colorado. There's some snow around, there's some rocks around. This is similar to what we're going to see on the surface of Pluto.
A traveler to Pluto would find that despite the snowy surface, it is a very dim place.
About 30 or 40 times further away from the sun than the Earth is. This means that the sunlight hitting the surface of Pluto is about 1,000 times fainter than it is on the Earth. It's maybe about the same brightness as being outside under a dim street light at night. You could probably, you could take a book, you could probably read it there. Take a headlamp though, take a flashlight, it'd help out.
Its distance from the sun also makes Pluto one of the coldest places in the solar system, with a bone-chilling average temperature of -388 degrees Fahrenheit. And because of its small size and low density, gravity on Pluto's surface is far weaker than on Earth.
Now, some things are going to be a little easy to do on Pluto if you're really into rock climbing. I'm doing some vertical climbing here. Well, it's always exciting, but gravity is always the challenge.
Pluto's gravity is roughly 1/15 of the Earth's.
It's not like if you're standing on the surface, you would float away. Now, if you fell off that face when you were climbing up Pluto, you'd still want to have your rope there. You'd still accelerate down to the surface. So don't leave the rope at home.
Scientists would love to chip away at the surface of Pluto because hidden within its rocks is a whole missing chapter in the history of our solar system.
Pluto's a great planet. I mean, it's what I think is really great about it. It's sort of the ultimate time machine in our solar system. It really shows us what the environment of the solar system was like 4.5 billion years ago when it's formed. The surface there is much more ancient than you're going to find almost anywhere else in the solar system. And if you're looking for rock on the Earth has been around for that same time period, 4.5 billion years or so. But if you're looking for rock that's that old on the Earth, you're not going to find it. And that's because the Earth is sort of constantly recycling its material. We have plate tectonics going on that sucks all this material back into the mantle. You have volcanism going on that pumps out new material and processes the surface. So it's really a much younger surface on the Earth compared with the ancient surface that we're going to see on Pluto. The rocks that we're sitting on here have been processed by the high pressures in the Earth. On Pluto, it's more primitive.
Primitive, but far from pristine. Pluto is likely riddled with impact craters.
Impact craters are caused by asteroids or meteoroids impacting the surface. These are essentially pieces of the solar system that were never made into planet. Out of the surface of Pluto, you don't have an atmosphere, you don't have glaciers, you don't have winds, you don't have rain, you don't have erosion. And so the one dominant feature that you see on the surface is probably going to be a lot of impact craters.
Pluto's pockmarked surface undergoes a transformation as it orbits near the Sun. Under the additional heat, some of the frozen gases evaporate to form a temporary atmosphere. As Pluto recedes from the Sun, the gases freeze again and fall back down to the surface. For more than 75 years, this far-out icy object staked its claim as our 9th planet. So why is this little piece of snowy rock now causing such controversy? Why was Pluto kicked out of the solar system's most exclusive club? It's a quiet office at the Caltech campus in Pasadena, California. And it was from here that Pluto's demise as a planet began. But astronomer Mike Brown was never looking to destroy a planet. Equipped with Palomar Observatory's 48-inch telescope, he was seeking out Pluto-sized worlds at the far reaches of our solar system. And in 2005, he found one. An object bigger than Pluto, with its own moon, both orbiting the Sun.
When I first found this thing that's bigger than Pluto, I was looking through the images that the telescope had taken just before, and I found it in the screen and did a very quick calculation, realized it was bigger than Pluto. And the very first thing I did was picked up the phone and called my wife and told her I just found a planet.
Indeed, if Pluto was a planet, and for more than 70 years it had been, then why wouldn't Brown's new world be considered a planet too?
I thought it was the 10th planet. For a long time, that's how I described it. It was a planet, and so I definitely felt like I had found the 10th planet. It's 5% bigger than Pluto. It's probably made out of the same materials on the inside, rock on the inside, ice on the outside, and a little thin layer of frost on the very outside that sometimes puffs up into an atmosphere and sometimes doesn't. Very similar to Pluto in that way. It has a moon that goes around it once every 16, 17 days. Pluto has a moon also, so it's, in many ways, I like to think of it as almost as twins. This is just the twin that just ate a little bit more when it was a baby, got a little bigger.
Brown considered naming his object Xena after TV's warrior princess, but eventually the name chosen was Eris. After the Greek goddess of discord. As it turned out, this name was entirely appropriate. The discovery kicked off a firestorm in the astronomical community. Now, the very definition of a planet was being hotly debated. Would Eris officially become our 10th planet, or would Pluto scientists objects be re-evaluated as a whole? The argument was brought to the table in a 2006 meeting of the International Astronomical Union in Prague. A vote was taken, and the term planet was defined scientifically for the first time.
Those who are in favor of Resolution 6A, which introduces this new category of trans-Neptunian objects with Pluto as a prototype.
The recommendation is that we consider Pluto and other similar trans-Neptunian objects to be in a special class.
We didn't reconsider Pluto's status because we learned anything new about Pluto that made it less interesting.
Instead, scientists say the issue was addressed because they learned about Eris and other large Kuiper Belt objects. The Kuiper Belt is a 3.5 billion mile wide region in the outer solar system near Pluto. It's home to hundreds of thousands of icy objects, the first of which was discovered in 1992.
So historically, we've thought of the outer solar system. You've got Uranus and Neptune out there. There are these big gaseous planets, giant planets. And then just beyond that, you've got this little straggler Pluto that doesn't really fit into the picture. Well, now when we found all these other Kuiper Belt objects, What we're seeing is that maybe Pluto is really just the first of these many, many bodies of the Kuiper Belt that are this wide diversity of small icy bodies at the outer solar system.
The result of the IAU vote stipulated that a planet is a spherical object that orbits the Sun and clears out the neighborhood around its orbital path. Since the area around Pluto is full of other Kuiper Belt objects, the new definition would leave Clyde Tombaugh's great icy discovery out in the cold. Pluto's 76-year reign as the 9th planet was over. Our solar system would now officially consist of only 8 planets. Objects like Pluto and Eris were given the new classification, dwarf planets. Dwarf planets possess the same characteristics as planets, but do not have a clear orbital path. Under the new definition, Ceres, the largest asteroid in our solar system, is also a dwarf planet.
We have this new terminology because there's more things in the outer solar system than we used to think. It's like all you could see was one skyscraper, and now all of a sudden you have a whole city in front of you. We have a whole city full of objects in the outer solar system now.
The IAU vote was meant to settle the debate on what constitutes a planet, but many scientists refuse to accept the outcome.
There are astronomers who want it to be a planet still, and they just keep ripping those scabs off whenever possible, and they want to keep it fresh.
I believe Pluto is a planet. And I don't think the question of whether or not Pluto is a planet is really that important. Fundamentally, it's not a scientific question, it's a question of names. But in a way, in an odd way, it's become one of the highly visible subjects of planetary science.
People always ask whether Pluto is a planet or not. There's not one easy dividing line. There's not where you move from being a planet over here to being a planet over here to being not a planet over here. Just like there's no real dividing line between a stone and a pebble. It's really more of a sociological question. It's a question of definitions of words rather than a question of science.
Although no longer officially a planet, scientific interest in Pluto hasn't waned. Even as the vote was being taken in Prague, a NASA spacecraft called New Horizons was already on its way to exploring this far-off world. The New Horizons mission will be the first spacecraft ever to visit Pluto.
By going to Pluto, studying Pluto, it's no longer a mission to a singular object, but it's actually a mission to one of a class of objects that we'll get to learn about.
But New Horizons needs to travel at warp speed, or a valuable research opportunity to study Pluto's atmosphere will be lost for at least the next 200 years. The New Horizons spacecraft is headed for a rendezvous with Pluto.
We have confirmation of spacecraft separation.
But scientists are trying to beat the clock. Because as Pluto recedes from the Sun, its 62-year-long winter is coming. And when winter comes to Pluto, the dwarf planet's atmosphere will freeze and fall to the ground.
If it collapses too much, it might just be a lot less interesting. You might not have as interesting chemistry. And we want to know what the temperature and the composition and the structure and the winds on the atmosphere.
To get there in time, New Horizons is blazing through the solar system at more than 45,000 miles an hour. That's 12 miles a second. At that speed, a trip from Los Angeles to New York would take about 3.5 minutes.
So this is the fastest spacecraft that was ever launched from the Earth. In fact, it took about 6 hours to get out to the 250,000 miles to make it out to the moon. You can compare that to the couple of days that it took the Apollo astronauts to get out that same distance.
New Horizons was passed by Jupiter in just 13 months, but the outer solar system is so big that it's going to take us another 8 years to get to Pluto.
Even with its unprecedented speed, New Horizons won't reach Pluto until July of 2015.
Pluto's just a big mystery. It's exciting to me that there's a spacecraft on its way there, and that in a few years we'll, this sort of blank slate of a world will be richly filled in with pictures and detailed data.
About 4 billion miles from Pluto, Uranus is a mesmerizing blue
And it's really strikingly beautiful and different from the other planets. It's a giant blue pale blue fuzzy ball sitting there in space against the darkness of space, and it's just that striking blue color and the almost pure featurelessness of it. It seems unreal. It looks as though it was sort of created by some movie special effects person, because how could you have a planet that large and that perfect and just this giant featureless blue?
Uranus is 1.6 billion miles from Earth. It has a diameter of nearly 32,000 miles, 4 times Earth's diameter. It takes 84 Earth years for Uranus to orbit the Sun. One day on Uranus is a little over 17 hours. If you weigh 150 pounds on Earth, you would weigh 133 pounds on Uranus. Named after the Greek god of the sky, Uranus has the most off-kilter axis of any planet in the solar system. At an angle of 98 degrees, the planet is actually spinning on its side.
What that means is that at one time of the year, only one hemisphere is pointing towards the sun. The other hemisphere is complete darkness. The time for Uranus to orbit the sun is about 84 years, which means that for half of that time of 40 years, one hemisphere is in sunlight and the other hemisphere is in dark.
It's like the Arctic Circle on Earth, except for it's the whole planet. That tilt is so extreme that in a sense, the whole northern hemisphere is the Arctic, and the whole southern hemisphere is the Antarctic.
Uranus owes its cool bluish-green color to methane. The methane absorbs red and orange wavelengths from sunlight, but reflects blue and green. And its soft appearance is due to something that's familiar to anyone who lives in a big city. Smog.
In Southern California, we're used to smog, which is photochemically produced haze material, which gives this hazy appearance in the atmosphere.
This is similar to the atmospheres of the 4 gas giants.
In the outer planets, there's methane, which is natural gas. Sunlight converts it to complex particles as well, which forms a haze, which is the reason the planets don't have a very sharp, but have a fuzzy look to them.
Scientists speculate that Uranus and its celestial neighbor Neptune formed the same way. As the early protoplanetary disk of gas and dust in our solar system settled, Jupiter and Saturn gathered up the most material and became the largest of the gas giants. As Jupiter and Saturn's orbits grew, they destabilized the planetary system as a whole. Dynamic interactions pushed Uranus and Neptune outward to the edge of the solar system at an accelerated rate, where they feasted on icy objects.
They have a lot of that initial gas, but they also gathered a lot of icy material and some rocky material in their formation. So consequently, although they have this surrounding envelope of hydrogen and helium gas and some methane, some nitrogen, some other stuff, they also have a lot of icy material in the inside.
These icy interiors have led some to call Uranus and Neptune the ice giants. But it's incorrect to imagine them as balls of solid ice that an astronaut could walk across.
Well, if we dropped an astronaut or a probe towards the center of Uranus or Neptune, well, first of all, they'd be in a lot of trouble. There's really no solid surface that they could stand on. There may be a small rocky core at the center of these planets, but the pressure that they would be experiencing from the atmosphere overhead and this liquidy, icy region would crush them. It would be millions of times the pressure that we have from our own atmosphere, for example. So they would be flattened well before they ever reach the solid surface.
While the other gas giants have wild weather patterns, Uranus seems to be relatively calm, and scientists think they know why.
Uranus is unique among the gas giant planets in that it is the only one that doesn't have an internal heating source. Jupiter, Saturn, and Neptune all have heat coming from deep within the planet, and that helps drive the circulation, and it explains why we see a lot of the banded structure that we do on those other three planets. Uranus doesn't have this internal heating source.
Uranus has another claim to fame. The way in which it was discovered by astronomer William Herschel in 1781. At the time, the only known planets were the 6 visible to the naked eye from Earth. But Herschel first laid eyes on Uranus through a telescope.
Herschel was an amateur astronomer, professional musician and optician, so he had the knowledge and ability to generate the best telescopes in the world at the time.
The discovery of Uranus was incredibly significant in the history of humanity because it was the first planet discovered by telescope, the first planet that the ancients didn't know about.
In 1977, NASA's Kuiper Airborne Observatory made another exciting discovery when astronomers aimed their their telescope at Uranus. They were planning to watch a fairly common astronomical event, the passage of the planet in front of a star. But as Uranus closed in, the star suddenly winked. In fact, it seemed to flicker on and off 5 times as it neared the planet, and then several more times as it emerged on the other side. What was the cause of this strange phenomenon? The flickering star was actually passing behind 5 planetary rings, features that had only previously been seen on Saturn. Subsequent observations from the ground, and then the Voyager spacecraft confirmed the ring's existence. And observations made in 2005 from the Hubble Space Telescope found a second set of rings, orbiting almost twice as far away from the planet as the previously known rings. Unlike Saturn's thick icy rings, Uranus's are dim and thin, comprised of dark, rocky dust. Some of Uranus's dusty rings were likely formed by the impact of a meteor or a comet with one of the planet's 27 moons. The inner rings could be the result of collisions between the moons themselves, especially the 13 that orbit in the planet's kinetic inner swarm.
There are a lot of inner moons around Uranus, moons that are very small and close to the planet. They tend to have very fast orbits on the order of maybe a day.
Other moons zip around Uranus in just 12 hours. By comparison, our moon circles a planet 4 times as small and takes 28 days to do it. With Uranus's moons speeding around the planet-like race cars, it's only a matter of time before 2 of them end up in another cosmic collision. Circling the planet Uranus is a swirling system of moons. Even within the last decade, substantial changes have been detected in their unruly orbits. Scientists believe it's only a matter of time before 2 of them cross paths.
We can be very certain that in a period of a million or a few million years, that some of them will collide with each other.
I'm thinking particularly of Cupid and Belinda, which are 2 small moons that happen to be orbiting very close to each other.
Traveling at just a few hundred miles apart, scientists expect that at some point, these moons, due to gravitational forces that they impart upon each other, will eventually collide and rip each other apart. It will be a bad day for the moons, but a welcome event for the planet's ring system.
The debris that's released from that can potentially generate a new ring around Uranus.
Uranus shares the outer solar system with its sister planet Neptune. A gleaming sapphire some 3 billion miles away from the Sun. With the demotion of Pluto, Neptune is now our outermost planet. Neptune takes its name from the Roman god of the sea. Neptune is 2.68 billion miles from Earth, measuring roughly 30,000 miles. Neptune's diameter is 4 times that of Earth's. A year on Neptune is equivalent to 165 Earth years, and a day lasts 16.1 hours. If you weigh 150 pounds on Earth, you would tilt the scales at 169 pounds on Neptune. Like all the outer planets, Neptune rotates much faster than Earth. And this rapid spin helps to create violent winds.
In fact, the highest winds recorded on any planet in the solar system are on Neptune. You have winds of sometimes over 1,000 miles per hour, and commonly 750 miles per hour, raging in that upper atmosphere. And we're not quite sure why, so there's a little bit of mystery.
What puzzles scientists is why Neptune's winds blow even stronger than those on the other outer planets, with speeds 2 to 3 times faster than in Jupiter's blustery Great Red Spot. JPL researcher Michael studies what drives weather on other planets. He's intrigued by Neptune's mysteriously strong winds.
If we were to put one of these windmills up on Neptune, depending on the altitude that we put it, we would either see motion similar to what we see now, or if we were to place it at the altitudes in which the winds are going 1,000 miles an hour, we actually might not see very much motion at all. And that's because the atmosphere is so thin that there's just not enough oomph and not enough force from that wind to actually turn the propellers of the turbine. So you might not actually see any motion at all. On Earth, we see high pressure and low pressure systems if we look at weather maps, and the same to an extent can be seen on the outer planets. We can't exactly identify a big H in this location or a big L in this location, but there are generally regions that are warmer and have higher pressure than other areas which are colder and may have lower pressure, and that generates the winds that blow from high to low.
A key factor in the creation of wind is an energy source to heat the air. On Earth, the sun provides this energy. But the windswept planet Neptune is 30 times farther from the sun than Earth, and it gets only about 1/900th as much solar energy. It's simply not enough to power Neptune's colossal winds. Scientists believe that Neptune gets its additional power from within. Measurements taken by Voyager 2 showed that Neptune radiates twice as much heat from its interior as it gets from the sun. The highest ratio of heat outflow to inflow of any planet in the solar system.
Neptune has a relatively large amount of internal heating, which is coming from radioactive decay of materials inside and other chemical processes that are occurring, and that releases a lot of heat from the inside.
Just why the interior of Neptune generates so much heat remains a mystery. It's led some to speculate that the planet is still in the process of forming, and the infalling gases are releasing heat as they are compacted by gravity. This internal heat source could also explain the convection of gases in Neptune's atmosphere that leads to fascinating cloud patterns.
There are many bright white clouds that appear in the atmosphere. There are different regions of very bright and dark banding. On the surface. So we'd be able to distinguish different latitudes by the brightness of the bands.
Scientists believe that the banding patterns have something to do with Neptune's cloud composition.
These are probably made of methane. And they move very fast around the planet as well.
Neptune's wind movement is unlike anything we are accustomed to.
These are giant storm systems. Storm systems that would dwarf anything that
1989, Voyager 2 snapped a photograph that shocked the mission scientists. Neptune had a huge storm, a great dark spot in its southern hemisphere, stretching 8,000 miles wide, large enough for our Earth to fit in the center. The storm resembled Jupiter's infamous Great Red Spot.
The Great Red Spot is a huge anticyclone, which is fed by many smaller storms that keeps it alive, if you like. Otherwise, it would dissipate and disappear. In the case of the Great Dark Spot, we believe it's more of an instability in the atmosphere, which rocks back and forth because of the flows in that very fast atmosphere.
Just 5 years after the spot was first discovered, scientists were in for another surprise. The Hubble Space Telescope turned its eye toward Neptune, only to see that the largest storm on the planet was gone. What happened to Neptune's Great Dark Spot? Within a span of 5 years, the largest storm on the planet simply vanished from the southern hemisphere. But that didn't mean the end of megastorms on Neptune. Astronomers using the Hubble Space Telescope observed that a new Great Dark Spot had appeared, but this time in the planet's northern hemisphere.
It seems that on Neptune, the storm systems that manifest as these big spots you can see with a spacecraft or a telescope, they sort of come and go on shorter time scales than, say, the Great Red Spot on Jupiter, which has been there for hundreds of years.
Not only are these storm systems transient, they're also eccentric. Scientists observed that the size of the Great Dark Spot oscillated by several thousand square miles within a span of just 8 days. The disappearance and reappearance and overall erratic movement make Neptune's storm systems some of the most unpredictable in the solar system. Similar to its outer planet neighbors, Neptune has a complex system of moons. "13 have been discovered so far. some of Neptune's moons may have originally formed elsewhere in the solar system.
Neptune's probably capturing these moons from the vast amount of material that's actually in our solar system beyond the orbit of Neptune and Pluto. There is a lot of very icy bodies, small bodies, planetesimals and other rocky things that pass through our solar system, and other debris. Every so often, some of this debris might collide with each other, and then they get pushed in toward the solar system.
Some of these icy bodies end up as comets. But if one is pushed in the right direction at the right time, it can be captured by a planet's gravitational pull, becoming a moon. Neptune's largest moon, Triton, is roughly the size of Earth's moon. It is the coldest object in our solar system ever observed by astronomers, even more frigid than Pluto.
Only 40 degrees above absolute zero, about minus 390 degrees Fahrenheit. So cold that the nitrogen, which would normally be in a gaseous form, forms an icy polar cap on this moon.
Triton's so cold primarily because the surface is so reflective. About 70% of the light that hits the surface of Triton is reflected back. And with that much light not being absorbed by the planet, it just gets very, very cold.
Triton could well be similar in composition to Pluto. We see ices on the surface there. One of the fascinating things that we see on the surface of Triton are actually plumes, essentially volcanoes. We see these plumes. We've actually seen them coming out in real time with the Voyager spacecraft when it went past Neptune and Triton.
Unlike Earth's volcanoes, Triton's geyser-like eruptions spew a mixture of liquid nitrogen, methane, and ammonia. And an upsurge instantly freezes as it rockets 5 miles high into its thin atmosphere. Once airborne, the ice can be carried along for miles by winds in the atmosphere before snowing back down onto the surface. Geological activity on Triton makes scientists wonder if there's water, perhaps being heated under Triton's icy exterior. And as the theory goes, where there's water, life could be present. If that's the case, Neptune's largest moon could be home to one of the biggest discoveries of all time. But due to planning and transit times, it will be at least 2 decades before we approach Uranus or Neptune again.
We've had discussions, but there are no current plans. We could with Voyager, where we just had a brief flyby, and we managed to collect a lot of discovery. But in fact, we need to get back to pursue those discoveries.
In the meantime, scientists will be focused on new horizons as it rockets even closer to Pluto. On board, in addition to a cluster of scientific instruments, is a small canister of ashes, those of Pluto's discoverer, Clyde Tombaugh, who died in 1997 at the age of 90.
I'm not involved in New Horizons missions at all, but I can tell you from my point of view why I'm very excited about it. We really don't have any good ideas of what the actual features on the surface of Pluto are going to be like. That's why these small-scale pictures, getting actual close-ups, is going to be so important.
As spacecraft, probes, and telescopes are sent to the far reaches of our celestial neighborhood, we come one step closer to deciphering the expansive universe. Our technology and our imaginations can help bring these far-off alien worlds to life. As we look at them with awe and wonder, we can only fathom what unexplored mysteries lie deep within.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Are we alone in the universe? Are we the only ones who look up at the stars and wonder, is anybody out there? Today, scientists quest for the answer in different ways. Some with massive radio telescopes, some with interplanetary and interstellar probes. If we find extraterrestrial life, what will it look like? Soft and squishy? Or will the first aliens we contact simply be self-replicating machines? Their biological creators having died off millions of years ago. Some of the top scientists in the world probe for answers in the search for ET. It is the question that has kept many people awake at night, staring at the stars, pondering the possibilities. In a galaxy filled with 1 billion stars, in a universe filled with 100 billion galaxies, are we alone? The incredible vastness of the universe is difficult to comprehend, but here's a way to consider it. If you were to shrink the sun down to the size of a marble and put it on a sidewalk in downtown Manhattan, the Earth would be a pinprick about 4 feet away. Mars would be 2 feet beyond that. The nearest other star where we might hope to find intelligent life, Alpha Centauri, would not be 10 or 100 feet away. It would be in Washington, D.C., 230 miles distant. And another star might be as much as 7,000 miles away. In Rio de Janeiro. But if we ever did chance upon voyagers from these distant points in the cosmos, what would they look like? Would they be basically the same as us? Would they be fundamentally different? Could they be perhaps so strange and unusual that they are unlike anything we ever dreamed or dreaded could exist? Many believe the quest for extraterrestrial life must really begin with intense scrutiny of how terrestrial life, life on Earth, might have begun. And in the early 1950s, 2 chemists at the University of Chicago advanced understanding of life's basic chemistry dramatically. Nobel laureate chemist Harold Urey and graduate student Stanley L. Miller concocted a batch of primordial soup They injected methane, ammonia, hydrogen, and water into a closed system of glass bulbs and tubes. These chemicals are thought to have been commonplace on early Earth.
If you put all of these things into a container and supply some form of energy to do some kind of reactions, what do they make? What kind of reactions go on?
Miller and Urey energized the mix with electrical sparks to simulate lightning. The results were, well, electrifying.
They got a brown sludge on the walls of their chamber. And when they started analyzing that brown sludge, there were lots of organic materials in it, and some of them were amino acids. Some of the precursors, the building blocks for proteins.
Proteins, of course, are in turn the building blocks for life. The Miller-Urey experiment had demonstrated that the precursors of living organisms could have gotten their start from a chemical reaction. And such reactions aren't limited to Earth. Methane, ammonia, hydrogen, and water are plentiful on other cosmic bodies within our own solar system, and many scientists believe throughout the universe. Indeed, noted astronomer Carl Sagan, speaking of the Miller-Urey test, stated that no other single experiment had done more to convince scientists that life is likely abundant in the cosmos. But the presence of water was key. Such a chemical reaction could not have taken place without it.
Water is very good at dissolving materials, much better than many other liquids. And so you can dissolve all sorts of nutrients and chemical, products, things that can act as catalysts. Things that go through the chemical reactions of life. So water is an excellent liquid for storing all of those chemicals.
On Earth, where liquid water exists, no matter how extreme the environment, some form of life also resides. It resides at ocean depths so great, sunlight cannot reach them. It resides in damp, rocky crevices, miles beneath the Earth's surface. And it even resides in the extreme salinity of an ancient California lake, with a salt content above 10%. That's 3 times the percent of salt in the ocean. But life on Earth also needs carbon, which was in fact the primary substance generated by the Miller-Urey experiment. All life forms as we know them consist in large part of carbon molecules.
Life needs some sort of ability to create long molecules that can store information. So carbon is amazing at building long molecules. So for example, the DNA molecule is sort of 1 billion base pairs long. If you stretched out a single DNA molecule from one of your cells, cells, it would be a yard long from a single one of your trillions of cells. And so you need something that can store the absolutely a huge amount of information that it takes to build a creature like a lion or a human or a tree.
But if life has taken hold elsewhere in our galaxy or beyond, would these conditions necessarily hold true? Would extraterrestrial life be water and carbon based? Would DNA shape intelligent life? And would the aliens look anything like us?
Maybe they would look a little bit like us. But that would be very, very coincidental. I mean, I just saw, a ground squirrel running behind a bush over here, and he inhabits the same planet I do. He's got DNA, probably 70% of his DNA is the same as mine. He doesn't look like me, so why would the aliens look like me? They probably wouldn't.
A scientist who has spent time pondering such questions and rendering speculative alien forms is Dr. Robert Hurt of the California Institute of Technology. Hurt is a visualization scientist who uses data returned by the Spitzer space telescope to render images of deep space objects and processes.
To try to find the best visual ways of explaining complex technical concepts, but through imagery. The planets that are being studied around other stars, the ways that stars in nebula form, processes going on in galaxies and the distant universe, all the way out to the edge of the Big Bang.
But for this program, Dr. Hurt has agreed to use known scientific data to render a speculative alien life form. For his alien world, he's chosen Jupiter. A real challenge, since Jupiter is essentially a giant gas ball.
Now here we have a place where there is no land to speak of. The atmosphere is made primarily of hydrogen and helium gas, though it's rich with organic compounds. And as you go deeper into the atmosphere, it gets warmer. And much higher pressures. So, as a kind of thought experiment almost, it was posed, what did you imagine living in an environment like that?
Referencing the only known model for life, living organisms on Earth, Hurt began by asking, what does life on Earth need?
You need sources of energy. You need the chemicals that life on Earth needs to build, the materials that it's constructed from.
On Jupiter, a primary source of energy is faint radiation from the sun, striking the top of the planet's atmosphere. And the only known source of chemicals for use as building blocks for life are the organic compounds swirling in the Jovian cloud blanket. Considering a potential life form that could take advantage of both long-term, Dr. Hurt remembered an idea originally postulated by Carl Sagan in the 1970s. The notion of a sort of living gas balloon. Such a creature could remain aloft in Jupiter's atmosphere indefinitely.
Now, of course, there's a problem in Jupiter, that Jupiter's atmosphere is already made of the lightest gas we know of, hydrogen. So you can't really make a lighter than hydrogen balloon. So if you want a balloon to be able to float in Jupiter's atmosphere, it actually has to be a hot air balloon.
Hurt has invented an extraterrestrial organism that is really more plant than animal. A balloon-like plant inflated and kept buoyant by hot air.
Now, it's going to be really expensive in terms of biology to generate that heat yourself. So instead, if we imagine a creature that has a very dark skin, very thin, that allows solar radiation to heat the gases inside, you might be able to create something that will levitate, at least during the daylight hours, just by absorbing solar radiation.
At night, the plant would lose its heat source, but Dr. Hurt has allowed for this problem in the creature's design.
It also has a shape that is well adapted to act kind of like a parachute that can ride thermals when it's not able to heat its own gases and float like a balloon. So in the nighttime, it might sink down lower into the atmosphere, but by finding thermals, it could ride this up like a glider almost.
Time spent at lower altitudes would actually be beneficial for the creature. It's here that its food is most plentiful.
I've given it a kind of air root system that hangs at the bottom. When it sinks into the lower parts of the atmosphere, it can screen out, pull up some of those organic compounds we know exist in the atmosphere of Jupiter.
Of course, Dr. Hurt's creation of the Jovian balloon plant represents nothing more than an entertaining exercise in extreme, though science-based, speculation. But the possibility that some form of life might actually now exist on other cosmic bodies in our solar system is very real to many astrobiologists and geologists. And one such body is right next door to Jupiter. the ice-covered Jovian moon, Europa. $370 million miles from Earth, orbiting the giant gas planet Jupiter, is the most likely harbor for extraterrestrial life in our solar system, Europa. It's an ice-covered ball about the size of our moon, about 1/4 the size of Earth. Scientists believe the ice on Europa is covering a global ocean of liquid water. A convincing indicator is that Europa is a conductor of electromagnetic energy. It conducts the magnetic field generated by Jupiter.
This conduction is the signature, or we think it's the signature, of salty water inside Europa.
It's believed that the water layer on Europa might be as much as 100 miles thick.
Now remember, Europa is similar in size to the Earth's moon, so that means that even though it's a smaller body, it actually has twice the amount of liquid water of all of the oceans on Earth put together.
And of course, liquid water is what makes life possible on Earth. So scientists who make it their business to quest for extraterrestrial life are keenly focused on the study of Europa. But how could liquid water, which freezes at temperatures below 32 degrees Fahrenheit, exist on a moon 5 times as far away from the sun as the Earth? Europa orbits Jupiter in an elliptical pattern. Sometimes it's close to Jupiter, and sometimes it's farther away.
When it's close to Jupiter, it gets stretched by Jupiter's gravity. It's an effect that we call tides. And when it gets further away, it's stretched less. So that means that the body of Europa is continually worked.
Friction caused by this stretching generates heat, just as a rubber ball heats up when it's squeezed repeatedly. At the planetary scale, this process is called tidal heating, and it creates enough heat, possibly, to keep H2O miles below the surface of Europa in liquid form. It also appears that this stretching causes fractures in the Jovian moon's icy crust.
Imagine if you were trying to change the shape of an egg. What would happen to the shell? The shell would crack. And so when we look at the surface of Europa, we see lines all over the place, which are almost certainly marking the locations of cracks.
the cracks appear to open and close frequently, and the potential for these cracks to allow subsurface water to interact with the surface has important implications for the possibility of life on Europa.
Water from the ocean is going to rush up into the crack. When it rushes up, it's going to freeze, start to freeze. A few hours later, when the crack closes, it's going to squeeze that slush up to the surface. And so wherever we see these lines on Europa, there are double ridges, one ridge lining along each side of the crack.
Most of the water, no doubt, sloshes back down out of the crack. To the ocean below. It's likely to carry with it some of the building blocks for life that have seeped down from the surface. The top of Europa's ice layer holds oxygen. It's been separated from the H2O in the ice by charged particles in Jupiter's magnetic field.
In addition, the surface of Europa likely has organic compounds that come down from comets and bits of comets. So again, the surface has another ingredient that's important for life.
Dr. Richard Greenberg of the University of Arizona has graphically depicted how potential life forms might take advantage of the ecosystem created by a crack in Europa's icy crust.
Although the outer few inches would not be a good place for life to live because of radiation, once you go down just a few feet, life would be safe from radiation and also would get enough sunlight for photosynthesis. So you could have an organism at that level that photosynthesizes, and it would be connected to the ocean by this tidal water that rushes up and down every day.
A day on Europa is much longer than a day on Earth. About 3.5 times the length of an Earth day. Time for mobile organisms to venture into the fissure.
You could imagine other organisms that grasp onto the walls of these cracks and just exploit the flow of ocean water coming past them every day.
Even mollusk-like or jellyfish-like creatures might rise with the water into the cracks to take in fresh nutrients from the surface. Life in Europa's ice-covered oceans may also draw energy and nutrients from a place other than the icy surface. It's possible that residual heat at Europa's core has resulted in deep-sea hydrothermal vents. On Earth, such vents host multiple forms of exotic life.
What happens is that reducing water that's very hot and has lots of heavy metals comes out through the groundwater and is injected into the ocean itself. And there's a huge gradient in the chemical composition that life can feed off of. This chemical source of energy allows huge populations of bacteria and other very small life forms to exist, and there's a whole ecosystem, a whole food chain on top of that, leading up to fish and various worms that thrives at those locations.
In recent years, talk has arisen of sending a lander to Europa that could penetrate the ice and probe for life. But Europa expert Richard Greenberg believes that a lander might uncover signs of life without penetrating the ice.
If we send spacecraft to Europa to look for life, it might be pretty easy to find it, easier than people have realized. Most planning has considered how do we get through these miles of ice to get down to the ocean. How do you drill through or melt your way through? It may not be necessary. If you can land in a place where liquid or ice has come up from the ocean recently, you might find signs of organisms in that ice. Or if you land really smart and find an active place, you might actually be able to sample real fresh oceanic water.
The risk in that case, some feel, would be contaminating the icy moon.
If we had microorganisms that stowed away on a spacecraft that landed on the surface of Europa, and those microorganisms found their way into the liquid water of Europa, we might later discover life on Europa that was life that we had sent there.
But elsewhere in our solar system, on another distant moon, earthly contamination isn't a danger. Life here would simply be too exotic. Since 2004, a NASA probe dubbed Cassini-Huygens has orbited Saturn, making multiple flybys of Saturn's largest moon, Titan. Titan is an enormous planetary body, the second largest moon in the solar system, 50% larger than the Earth's moon. If it wasn't in orbit around Saturn, Titan would be a planet in its own right. But most impressive of all, Titan, many scientists believe, could now, or at some point in the future, be an abode for life.
The geology is very much like Earth's. All the processes that we have on Earth, wind, erosion, lakes, volcanism, mountain building, impact craters. We find them all on Titan, and so Titan is very rich in terms of geology.
But at 840 million miles from the Sun, 9 times farther than Earth, Titan is beyond freezing. The mean temperature on its surface is almost 300 degrees below 0 Fahrenheit. It is so cold, and water on the surface of Titan is frozen to such an extreme state, it behaves like rock. The rocks in this blurry photo taken by the Huygens lander are, in fact, water. It is so cold that hydrocarbons that are gases on Earth, such as methane and ethane, are in a liquid state on the surface of Titan. The Cassini flybys have spotted them.
We're seeing a lot of what looks like organic materials on the surface, and we're seeing large bodies of liquid, but it's not liquid water, it's liquid methane with possibly some ethane dissolved in it. There are huge lakes on the size of Great Lakes or small seas.
Astrobiologists are beginning to entertain the notion that organisms could have developed in those lakes.
Life could be very, very exotic. We have been thinking of life in terms of water and liquid water, but could there be life in liquid hydrocarbons? Perhaps. Life on Earth exists in some very difficult places that you wouldn't expect to find life. And we call these organisms extremophiles. That's because they can live under extreme conditions. For example, here on Mona Lake, very alkaline lake, and yet extremophiles have been found living here.
Another possibility is that life formed much earlier in Titan's history, when a great deal of heat from the initial formation of the moon remained. At that time, conditions on Titan would have been very similar to those on primordial Earth.
There's a lot of water there, there's a lot of nitrogen, a lot of other things. So you've got warm water, nitrogen, carbon, and we think some of these chemical processes that went on Earth to start generating the biological, pre-biological materials that later on would be incorporated into life. That may have started on Titan also, with the same kind of chemicals present in a warm environment.
Some think it's possible that if Titan's core is still warm, microbial life, at least, might still be present deep below the moon's surface. Living organisms have been found thriving in damp rock crevices 2 and 3 miles below the surface of the Earth.
Now, if you go deep down into Titan, and when I say deep down, I'm talking about 50 kilometers or 100 kilometers, maybe even a couple of 100 kilometers. Just like Earth, as you go downward, it gets warmer. And it looks like probably at Titan, there are materials mixed in with the water, such as ammonia, that can act as antifreeze. And we know this liquid water is a wonderful medium for all kinds of chemical reactions, including the reactions that generate amino acids and other prebiotic chemicals.
At present, though, close observation of Titan's surface is limited. The moon is cloaked in a dense atmosphere of nitrogen and methane. The Cassini probe is equipped with an infrared imager, but photos shot in a visible wavelength are often much more useful to analysts.
You have to somehow get around this opaque atmosphere that's obscuring your view of the surface. But to really see what's going on the surface, and notably to get a really firm idea of what is the composition of all these different things that we see on the surface, it turns out we're going to have to go down there close to do that.
The Huygens lander has touched down on the moon and sent back images, but the lander is not mobile.
When you land on a planet, of course, that brings tremendous advance in terms of science, but it's only one spot. So how much of the Earth would you know if you landed on the Sahara Desert, for example? You wouldn't see the kind of life that we see here.
One possibility for exploring vast expanses of the Titan surface would be to use a craft that works much like a hot air balloon on Earth. NASA's Jet Propulsion Laboratory is developing a balloon craft that would carry both imaging gear and equipment for studying the Titan atmosphere. Engineers consider a balloon the most stable platform for such a mission.
If a balloon loses its electronic control for several hours, no big deal. You can have something on board that senses that and tells the balloon, okay, close your ascent-descent valve and just go to a safe altitude and sit there until you get further instructions.
But while complex missions to far-off moons within our solar system are exhilarating and often return great scientific insight, the promise of discovering more than primordial extraterrestrial life is slim at best. The hope of finding intelligent, technology-producing life seems greatest when we look beyond our solar system to neighboring stars. While we may never encounter such life, for most scientists who study the universe, the notion that it exists somewhere makes perfect sense.
Life tends to evolve to become more successful, and one of the things that makes organisms successful, it seems, on Earth, is to become intelligent. So it seems quite plausible to me that there are creatures that have some sort of intelligence on other planets.
If one of those starts out 1 billion years before our solar system started out, and it takes that one 1 billion years longer to get to that point, well, they're at the right time right now.
And at radio telescope installations across the globe, we Earthlings are listening for them.
Oh, well, howdy doody, boys and girls!
We have been sending signals into the void for decades. Every broadcast on this planet, every FM radio wave, every television transmission goes out into the infinite for all of eternity. Could anybody out there be listening? And how long would it take our radio signals to cover the distance? Let's consider once again the analogy where our sun is a marble on a sidewalk in downtown Manhattan. Alpha Centauri, the closest other star, is a marble on a sidewalk in Washington, D.C. And a more distant star is a marble in Rio de Janeiro. A rocket launching from Earth, the marble in Manhattan, would take 75,000 years to reach Alpha Centauri, the marble in D.C. That same rocket would take 2 million years to reach the marble in Rio, a star 100 light years away. Fortunately, radio signals are much faster than rockets. They travel at the speed of light. So rather than taking 75,000 years, a signal traveling from the marble in Manhattan to the marble in DC would only take 4.5 years. A signal traveling from the marble in Manhattan to the marble in Rio would take 100 years to make the journey. Some of our earliest transmissions might now be getting close. But what about the reverse? Could intelligent alien civilizations be sending pings toward Earth to see if anyone is at home? Scientists on Earth are listening, using technology originally developed for studying distant cosmic phenomena, like exploding stars.
Many phenomena produce radio waves, and by studying the radio waves, you can also learn something about, what's out there and how it works. So using radio antennas to study the universe, that's an idea that goes back to before the Second World War.
The huge radio antennas used today, called radio telescopes, are so advanced and so incredibly sensitive. They can easily detect the energy of a flea hopping.
They're just big reflectors, right? So the radio waves that are coming down and falling on the ground all around us, on the whole Earth after all, well, some of those radio waves will fall on these antennas. So they bounce off that big mirror, then they get focused to a very sensitive amplifier. And then the signals are sent via cables back into a control room that's right nearby here, where they have sensitive receivers to sort of analyze the radio energy that's coming in.
Dr. Seth Shostak is a senior astronomer at the SETI Institute in Mountain View, California. SETI is an acronym that stands for Search for Extraterrestrial Intelligence. The SETI organization also uses radio telescopes. But not for studying natural cosmic phenomena.
The very same technology can also be used to look for signals that are made not by nature, but by, well, perhaps E.T.
And how might one know the difference?
The kind of signal that we're looking for is what's called a narrow band signal. That is to say, it's just a signal that's at one spot on the radio dial, that it's at one frequency. That's the indication that the signal is made by a transmitter, not made by nature.
Of course, computers do the listening, not scientists.
We have these specialized receivers that do all the listening, and the computers are monitoring the receivers. So typically, we'll have receivers that monitor, say, 100 million channels at once. So if the computers see a signal that looks like it might be extraterrestrial, as opposed to a radar at the local airport or telecommunications satellite or something like that, then the computer will follow up on that signal, and if it's beginning to look like, yeah, you know, this might be the big one, then it'll call us up and draw it to our attention. So we don't have to sit there and be bored all the time.
To date, no such signal has been detected. But the SETI Institute presses on faithfully. Rightly so, in the minds of many prominent astronomers.
Absence of evidence is not evidence of absence. So we can't say, well, SETI hasn't found anything so far, so obviously there are no other intelligent civilizations out there. No, we can't say that, and I support their continuing to look.
There are hundreds of billions of stars in our galaxy and hundreds of billions of galaxies in the universe. Just by sheer weight of numbers, I would be surprised if there's not intelligent life somewhere else in the universe.
With so many possibilities, how do SETI astronomers determine exactly where to focus their telescopes and efforts?
You want to pick star systems that have a good chance of maybe having a planet something like this one, so that there's a greater chance that you have intelligent life. But we don't really know very much about what kind of planets these stars have. So we just have long lists, literally millions of stars relatively nearby our cosmic backyard, and we just work our way through them.
And what would happen if one day a SETI radio telescope picked up a signal that looked like it could be an alien transmission?
One thing you would certainly do if you picked up a signal is say, look, I'm not going to believe it until somebody else can see it as well, because, you know, there could be bugs in the software or hardware that are fooling you here. So what you would do is, at the point where you thought this looks real, you would call up somebody at another radio observatory where they also have antennas just like this, and tell them, look at that part of the sky over this range of radio frequencies, this part of the dial, and see if you find anything. And if it were confirmed at 2 or maybe 3 observatories, I think at that point you could safely go and have your press conference.
But what if our first contact with ET isn't through radio signals? What if ET arrives in a form we don't recognize? The first alien delegation could reach Earth in the form of machines, so tiny human beings cannot detect them with the naked eye.
Step forward. You speak English. We speak every language.
the 1950s at least, science fiction films have consistently depicted potential alien beings as human-like.
Homo sapiens, slaves.
One particular alien form has been widely popularized in recent decades. UFO enthusiasts believe the U.S. military recovered bodies from crashed alien spacecraft in the 1950s. These alleged extraterrestrials are essentially frail miniature humans with oversized heads.
Little gray guys that usually have big eyes, they don't smile a whole lot, but they're always sort of soft, squishy organic things. Maybe they don't have DNA, but they're biology. They're alive.
It's an easy anatomical form for human beings to comprehend and accept.
Is that what E.T. would really be like? Maybe. I mean, you know, it's a good guess. That's what we're like. But on the other hand, I think that within 100 years, we may invent thinking machines. And if we can do that, if we ever do that, the aliens might have done that a long time ago. Keep in mind, the universe is a lot older than the Earth is, so they've had plenty of time.
Hello, Kismet. You gonna talk to me?
While the notion of thinking machines might sound far-fetched, some futurists believe such machines are just around the corner.
We're shrinking the size of transistors on an integrated circuit. So every 2 years we can put twice as many on a chip, and they run faster because they're smaller. And this has been true now for decades. I can carry in my pocket today a computer that's thousands of times more powerful than the computer that all of us, thousands of students and professors, shared when I came to MIT in the 1960s.
Ray Kurzweil is convinced that the power and speed of computers will shortly surpass that of the human brain.
If you take the most conservative estimate of the amount of computation required to simulate the entire human brain, which is 10 to the 16th calculations per second, there are other estimates that are lower than that. Take the most conservatively high estimate. We'll have that for $1,000 by 2020. And we'll have it for $1 by 2030. We'll have that in the supercomputer actually within a few years.
Kurzweil predicts that in the near future, tiny supercomputers will be integrated into the human body to bolster some of its weaknesses.
We've already started. I mean, there are people walking around that have computers computers in their brains that replaced a portion of their brain, like Parkinson's patients. And there are already these devices actually can download new software. So you can download new software to the computer in your brain from outside the patient. This is today.
It doesn't stop there. As technology marches forward, microscopic computer-driven machines called nanobots will be capable of performing a wide variety of maintenance tasks within the human body.
And we're ultimately going to be able to send these devices through the bloodstream, and we'll have billions of these blood cell-sized computers and little robots inside our bloodstream. They'll keep us healthy, and they'll be interacting with our biological neurons. So we go out to about 2030, the common man and woman will be part biological and part non-biological.
But perhaps Kurzweil's most radical prediction is that computers will ultimately allow human beings to transcend their biology, shed their bodies altogether. Computers will scan the neurological functions of a person's brain and upload the individual's knowledge, experience, and personality to a storage device.
You'd have to, in real time, go inside my brain, probably with nanobots, blood cell-sized scanners inside the bloodstream, and send billions of them into my brain through the capillaries, and they would scan all the different neurons and gather every detail about me, all the neurotransmitters and ion concentrations and interneuronal connections, and every detail that makes me me. And I think that will be feasible. That'll take longer, you know. Maybe that's 40 years from now or more. But we'll get to a point where you could actually capture every detail about a person and then recreate that personality.
The implications are, of course, staggering. Chief among them is the possibility of immortality.
You can back up your files. If the hardware dies, it's not the end of your files. You just copy them over to a new machine. The whole personality of your machine can be preserved. You can make another copy of it.
And the machines themselves will be intelligent enough to self-replicate and steadily improve their design.
We see self-replication in computers. For example, the software virus. That's an entity. It's not physical. It's just a piece of software, but it's actually able to copy itself. So someone can put out one software virus, and it's busy copying itself and then moving through the internet, and pretty soon it can be on a billion computers. So that's self-replication.